Welcome to week 6. This is going to be Introduction to Simulations. So last week we talked about data and control structures. This week we're going to get a little bit farther into simulations. So you did have an example last week of building a very simple type of simulation. We're going to continue to build that through this week. So here are the weekly learning objectives. Those are again repeated. There's 6 different things we're going to have to do. First of all, standard deck of 52 playing cards, create a simulation to calculate the probability of getting an ace. So remember, with 52 cards, there are 4 aces. Second thing, create 2 simulations of functions to perform coin tosses of a binary output. So think of a coin toss that's either heads or tails. So one, you're going to use the sample function, which we used last week, and then the other one, you're going to be using the Binome function. Third, we're going to create a function to calculate the probability of a discrete distribution. There's examples in the text for doing this, as well as in the R cookbook. You can find several of these online too as well to kind of get your mind thinking about that. I'll walk you through some things here. Fourth, create a probability and a distribution. Build a function that will determine the corresponding quantiles. So it's going to be breaking quantiles. There's probably 3 or 4 different ways of doing this too as well. If you're quick, you can pick it up that there's a library that'll break things into quantiles. You may just go ahead and rewrite one on your own. Again, this is another example where there's an example in the textbook as well for you to take a look at. Number 5, calculate a z-score. You can calculate a z-score using a formula. You can calculate a z-score using a function inside of a library. There's several ways you could solve for that one. But the bottom line, calculate a z-score. And then finally, using the simulation you suggested in the discussion, create an R program to build that simulation. Include graphs and statistical information as part of that. So question 1, card simulation. Again, you can use the modulus operator, which is, again, the percent sign. If you use that, what you're going to look for here is you're going to try to find one of the 4 cards. So big hint right here. If you're thinking about the number of cards, 52 cards in a deck, if you just make the cards aces that are divisible by 13, 26, 39, and 52, those would all be identified as aces. So using that same technique that we used before with the modulus operator, if you did something like this, you'd be able to determine whether or not you found an ace. And so then it's simply building a wrapper function with a for next loop on the outside of it. So that one would be very, very simple in order to solve. So let's just say we had one built up. Let's say I wanted to test it. Here I'm going to go ahead and create a data frame, and I'm going to make attempts. The temps is going to be the string which I use in order to label these, and then the values are going to be actual calls to the function itself. So in my case here, I wrote a function called draw aces. I'm going to run draw aces multiple times. I'm going to store that using a concatenation, store that inside of a string, and then turn around and pipe that into a data frame. Then I can use this ggplot call in order to build this graph. The graph is not necessary, but if you do want to reuse this piece of code, if you wanted to use your function, whatever your function's name is, and you wanted to execute it multiple times, just make sure that you have the same number of labels as you do calls to your function. This code right here, more than happy to let you use that for your solution, because the core of your solution is really what you do inside that draw aces. So here's an example of one. We can see the higher number of attempts that I've got. You can see it's kind of leveling out. You can also see a printout of the data frame so I can see where those are at. And if you look at here, the probability of getting an ace starts to increase. It starts to level out at about 0.76%. The second one, the coin toss simulation. So again, think about this. This is simply doing a binary choice. So a pseudocode that you could use is put a for next loop. Inside the for x loop, do a sample. For the first one, you got to use sample. So if you use sample, if you do 0 to 1 and you do 1, each time it runs through that for next loop, it's going to just select one value. And so then if you store these up, then that's how you could get to the final solution of it. I did one here and also provided a graph for it. If I do the graph, I can see roughly half the time we're getting heads, half the time we're getting a tails on a simple sampling. So that would get points for the second one here to develop something that's very similar to that. If you wanted to just print it out similar to what you see on the data table here, of just showing the value and the side, whether it's heads or tails, that is also okay. Now for using our binome, our binome, it'll be n is the number of observations. Size will be the total number of size of the number of trials, 0 or more. And probability is the probability of success. So let's assume if it's a heads or tails, it's a 0.5. It's a 50-50 shot you're going to get per flip. This can also be rewritten in a line that's about 3 lines worth of code. So if you look at that statement, it's going to be something relatively like this that you're going to have to write for that R binome statement. If you do that, then you're going to end up having something very similar to as well. So that's the heads, the tails. So that'll get you through the second question. The third question is that discrete distribution. So here we're going to use the D binome function. And D is the vector of quantiles that we're going to use. Size is the number of trials, 0 or more. And then probability is the probability of success. So if you just saw from the previous binome that we used, it's very similar in calling it. For my function here, we're going to go ahead and use X, N, and P for the 3. I'm just basically taking the first, the number of trials, N, and P for the probability that it's going to happen. Now, big hint. You must use this formula. This is the formula right here. So if you use my key here of X, N, and P, X, N, and P, you must use this formula. That's simple. So if I have a discrete distribution, I want to test it. Let's say we have one vector. Let's say we have 10 trials and a probability of 0.06. I can display this in a test right here. I can just print out the results. And here we go. We get it. Again, I would strongly suggest you read your text because your text has a more detailed layout of how to do a function like this. So you can find your solutions, most of the solution in the text, and then it's just simply putting some of that together for you. Question number 4, probability of a distribution with a quantile. This is really looking to split on quantiles. So for this, I'm going to use this myQuantile function that's out here. And I'm providing this to you again because it's more of to try to get the splits on the 4 quantiles. So the code piece of it, can you understand what's going on inside of the code? There's also a couple of really nice libraries that do this for you too as well. This function here was taken from out of the book. So if you want a more detailed description, right here is a description of quantiles. But basically what I'm looking for here is I'm looking for the breaks on the quantiles and the 0.25, 0.5, 0.75, and 1. So each of the 4 quantiles I want to see a break on. The output should look something like this. Now you can test this also as well using my numbers. So if you use the same type of numbers you see here, you should get the same type of results back out of it. So it's basically just taking that vector and splitting it on the quantiles. 25%, 50%, 75%, and 100%. Multiple ways you can do that. Calculating a z-score. This one should be very simple, actually. Here's a more detailed description right here, and Data Science Central has a good rundown of what a z-score is. But the z-score basically boils down to the sample minus the mean divided by the standard deviation. So an easy way to solve for this one is using the scale function. Look it up. You could also write this out in just a very simple 1 or 2 statement, response to as well to calculate that z-score. That's what I'm looking for. Here are some check numbers that you can use for that. Finally, you suggest as part of your discussion, you're going to suggest a simulation. Do not suggest an inventory simulation similar to what I'm showing you here. If you do, you won't get any points. So just be fair warned on that. This gives you a more detailed breakdown of what I'm doing in this one. Much as we talked last week about the keeping it simple, I'm just using results to paste back. I'm just printing out the results of my simulation as part of this. So first thing I'm going to start off with is my wrapper function on the inventory simulation. I'm going to have a number of orders to simulate, and I'm also going to have a total percent of the inventory in order to have inside of a buffer. So this is comparing number of orders coming in versus the number that I have available in the inventory. Very simple type of solution. It involves some basic calculations. I do put in a quantile in here, but it's basically just looking at the differences between the two of them. What I got is, as far as orders, decrement orders, etc. I do produce a histogram. Histogram is probably the easiest way to produce a graph. You can also use ggplot in order to do that. Sky's the limit as far as your particular simulation. This is a very simple one that you could take a look at, run through, and see if you have questions on. So in this case here, I'm going to test it out with a number of orders of 10,000 orders. I'm going to turn around and look at a percentage of the inventory at 99, 95, 90, and 50%. And so then I'm looking at the total fulfillment times produced out of it. So there's the output of it, and here are the histograms that go with it. And you can kind of see that I also run several different versions of this. The code is included above, so you can walk down through the code at your leisure and kind of work through that a little bit. But here again, 10,000 and a 0.95%. Here is 10,000 and a 90%. And then so on and so on. And so by doing that, it provides the solution to the final question. This can be as complex or as simple as you would like to make it. Again, the full points is create a simulation, make sure it executes without issues. It should perform the action that you discussed in the forum. Do not use an inventory fulfillment system. Okay? So that's the entire thing. I will also drop this, with this video, I'll also drop off this PDF that would allow you to kind of scroll through it and review all the pieces of it. But that's what you need to do for week 6 in order to get full points on it. Any questions, please reach out on the forums, also in email. We have office hours Tuesday nights and Thursday nights. Tuesday nights at 8 Eastern and Thursday nights on 7 Eastern. Tonight I'll be online to answer questions, either if you had questions from week 5 or from week 6. Have a good week. Thanks.